Hello and welcome back to Formal Intelligence. Addressing complexity is one of the key aspects of doing formal verification of any design of reasonable size. In this video, you'll see three broad categories of addressing complexity. I have categorized them into basic, intermediate, and advanced. First of all, how do you know if you're facing a complexity issue? These are the signs. If your tool starts crashing often, mostly complaining high memory use, or in the long run, if you run it for, let's say, for a day or 2 days or even 3 days, and you see so many properties which are hitting certain bounds and but they're not proceeding beyond that point. In short, you have so many undetermined properties. And in another category where you have cases where the precondition or the cover for that property itself is not hit. These could be the signs where you need to start looking at fixing the complexity issues in your formal verification environment. Let's look at the basic things that you can do to address the complexity. One would be to reduce the complexity of different blocks inside the design, size of different blocks inside the design. I mean, for example, if you have a 5.4 which is of uh, depth 16, you could try running the checks for a size of 2 or even 4 and so on. And another category would be over constraining the inputs. For example, if your design is accepting a lot of traffic, initially it makes sense to reduce certain traffic and allow only uh, part of the traffic. You can add assumptions where what I mean is if you can write assertions, then you can convert them into assumptions as required. Another category would be to add black boxes. So there are certain checks which does not really require some blocks inside the design to be there while you do that check. In that case, you can do black boxing, wherein you will replace that block with uh, um, with essentially no logic at all. So you'll drive the outputs coming from that block freely so that it can take any value. And this is something related to cut pointing. Something related to that is also called cut pointing. You can pick certain inputs, certain internal signals in the design, and then let it take any value rather than being driven by a complex logic, which will have a big cone of influence, adding to complexity. Once you have done all that and you still see complexity issues, it's time to do some intermediate complexity reduction techniques. One of them is case splitting. If you have a property which is which can be kind of decomposed or rather split into different cases, then we can do that. We'll deal with that. We'll discuss about that more later. One simple example would be you have an ALU where your opcode can take different values like addition, subtraction, multiplication, shifting, etc. And you want to focus on only one at a time. Let's say you allow the opcode to take a value of just addition and then you do the check, then just subtraction and do the check, and so on and so on and so forth. Second category is doing abstractions. Abstractions can be broadly categorized into four: initial value abstraction, reset abstraction, and then abstracting counters and big multi-dimensional arrays in the design, and then specifically abstracting blocks like memories. By abstraction of these blocks, what I mean is to replace the memory with a simpler model. For example, you track only one entry in the memory or one entry in the FIFO. By counter abstractions, what I mean is instead of letting a big internal counter in the design take all the values ranging from 0 to, let's say, 63, passing through all the intermediate values. You could say that, hey, you can start the counter from 0, but it can jump values from, let's say, 3 to 33 and then maybe to 64, and then so that the design can reach the interesting counter value quickly instead of passing through all the increments, because every increment will count to clock cycles and then which adds to complexity. And there are two other things called initial value abstraction, reset abstraction. Here, um, you are letting the design take internal design elements take interesting values out of reset as quickly as possible, maybe in a cycle itself, instead of uh, instead of consuming, let's say, 10 clock cycles out of reset to reach to that particular state. So all these abstraction techniques are used to get a quicker failure or to get go to deeper bounds where you can ensure that bug whether bug you can check whether bugs are present or not. Let's say we tried out all the techniques in basic and intermediate complexity reduction methods. Then if you're still seeing issues, then it's time to try out some advanced techniques. One thing would be based on your knowledge of the design. Now we can decompose a property into multiple smaller ones, and then if all of them are getting proven, um, you could imply that the main property is getting proven. Then there are techniques like assume guarantees, wherein you are first proving a smaller property, and then um, if it's proven, then different in a different environment, you can assume that property and then use it to prove some other some other properties which is more complex. Then there are approaches like there are semi-formal approaches which include things like waypoints. Waypoints are some hints which you can provide that will kind of guide the model checker in a direction where a bug could be found. Writing waypoints or identifying waypoints requires the designer or the formal verification engineer to have a very good knowledge of the design. If you provide wrong waypoints, then you might be searching some areas in the design where uh, you might never find a bug or there are no interesting bugs. And the final one is bug hunt. There are many bug hunt techniques uh, which are available in the state of the art tools. Some interesting ones would be to check around a particular trace. Let's say you know a particular scenario. Let's call it a cover trace. If you know that already and you are interested in ensuring that some other check does not fail within the vicinity of that trace, then you can feed that cover trace and ask the tool to do bug hunt around that trace. Another interesting one would be to try for certain bounds. You tell the model checker or the tool to quickly go to a bound 60, let's say, and then try out from bound 60 to 70 in increments of, let's say, 1. So it will, in a particular run, it can start from 60, then 61, 62, and 63, cover bounds up to 70. In another experiment, you can try out maybe from 90 to 100, and so on and so forth. These are the three broad categories of complexity reduction techniques. In this section, we are going to cover one of the basic techniques, which is parameter reduction. Parameter reduction is simply the way of passing a smaller parameter through tickle so that you can override the higher value which is already set in the RTL. This reduces the state space and hopefully this will take you to deeper design bounds quickly. There are certain pitfalls which you should be aware of while doing parameter reduction. Let's say there is a FIFO and then you're reducing the size from 16 to 4. But if there are some bugs which are uncovered only when the FIFO size is higher than 8, then you'll be missing that bug. So it's important to talk to the designer or understand the design well enough to ensure that the parameter is covering all the interesting scenarios. And once you have done enough experiments with smaller parameters, it's important or it's desirable to run regressions. By regression, what I mean is nightly runs or longer runs, wherein you can pass different parameters and ensure that all interesting parameter sizes are covered in the regressions. Only after that you can say that you can sign off the particular design is informal using parameter reduction. Now we will see another a particular example, in fact, the example of the FIFO itself, where we will do the parameter reduction and to see the impact of changing the parameters or rather overriding the parameters in Tickle in getting deeper design states faster. Let's see a case where we apply parameter reduction in a FIFO. In this folder, I have .sby file, which is used to run model checking in a tool called EOSIS, and there is a design FIFO. Let's first look at the design, or maybe the SBY file, where there's a particular section where I'm overriding a parameter max data, which is essentially the number of entries that can be stored in the FIFO, to 4, which is not the case in the actual design. It is a much bigger value. For example, in this case, we have max data 16, maybe where it is instantiated. 16, where it is instantiated, can be 63 or even higher values. And in the formal verification setup, I have a cover which is essentially checking when the full signal of the FIFO is getting high. So if we have a check which is whose precondition is directly decided by the signal going high, full going high, then the number of cycles taken out of reset to reach to full state, full equal to 1 state, is very important, and it adds to the bound of the check itself. Now, if I keep the value of the max data at 63 and try to reach this cover, let's see how much time it takes, and then compare it with a reduced parameter. Let's open terminal from here. From here, let's go to EOSIS environment. That's how I do it. If you do this, you are into OSIS cat suite environment, and as you see, you have .spy file here, which can be called like this. You can see that the cover took some time to reach to pass. Let's see the cover trace using GTK wave tool. Let's plot the clock and let's plot the full signal. It took this many number of cycles and 600 nanoseconds to reach. Sorry, this is just a clock period. You can ignore that for now. It took this much time to reach to the full state. So if you're just interested in full going high, don't care about what comes in between, we might as well reduce the size of the FIFO and reach full equal to 1 state much quicker. How do we do that? Let's override the parameter max data in the tickle to say 4 and run it again. As you can see, the cover reached in 5 steps. You can see that the trace is already here. Let's see how the trace looks like. And here's a clock, and here's a full signal. It reached much quicker in 4 cycles. That's a general idea of parameter reduction. You can reach interesting scenarios quicker by reducing the parameter. Thanks a lot for watching. We will cover many other parameter reduction techniques in the subsequent videos. Stay tuned to the channel and subscribe to support. Thanks a lot again for watching. Bye.